Number 23. A 0.25 kilogram aluminum bowl holding 0.8 kilograms of soup at 25 degrees Celsius is placed in a freezer. What is the final temperature if 377 kilojoules of energy is transferred from the bowl and soup, assuming the soup's thermal properties are the same as that of water? Explicitly show, I'm going to do my own steps. So what we realize is this problem's hard. That's what we realize. And there's some thinking that has to go into this ahead of time. Let me explain why. So you're putting, here's your aluminum's in black here, and then the soup is in yellow. You're going to take this bowl and you're going to put it into a freezer. All right? And they're asking us to then calculate, and they're telling us how much energy is being transferred. Okay, so that's cool. And they want us to then find the final temperature of, right, this whole system. So just consider that the aluminum and the soup, right, are basically together. We have to calculate them separately, but they are one system. The problem here is, let me actually first ask you a question. Does this freeze? How do you know if it freezes? Does it freeze? Well, you might say, well, it's placed in a freezer, so it should. Well, yes, but as soon as you put an item in the freezer, does it freeze? No, right? It takes some time. Now, I don't know how much time has passed, nor do I really have, I might have an idea, but I'm not really certain, let's just say at the moment, if this amount of energy would allow this soup to freeze. Meaning, if this soup and aluminum lost this amount of energy, will it freeze or will it not freeze? That's the first key critical question. And the reason why we have to answer that question is because there will be a phase change then associated. If this thing freezes, we have to then take into account a phase change, the energy released during the phase change as well. So either this problem becomes, see, if we think about the continuum, either this problem is a one-stepper or it's like a three-stepper kind of. All right, we got the three phases: solid, liquid, solid, liquid, gas. We're starting the problem here. We're saying that the soup is basically the same thing as what do you call it? As water. So we're starting the water freezes right at 0 degrees Celsius. We're starting the problem at 25 degrees Celsius. So we're starting it right about here, 25 degrees Celsius. So the question is though, what is the final temperature? Does it go past the freezing point and does it turn into a solid? Or does it just reach the freezing point? Or does it not even reach the freezing point? Maybe it only goes, maybe it only reduces down to 10 degrees Celsius. The problem is, though, depending upon my answer to that question, will determine how many steps I have to do. So I actually have to think. I can't really calculate it yet because I don't know if there's a phase change or not yet. So the first key critical question to this problem, and that's why it's difficult, is to ask yourself, is there a phase change? Okay, so that's actually part A or part 1. Phase change. Question mark. So how can we determine if there's a phase change? Well, why don't we determine the amount of energy that has to be released for this system in order to get to 0 degrees Celsius? Okay, let's do that first, right? And then you might see how we might then determine whether it's going to freeze or not. So if I'm talking about the Q of the total system, okay, let me just Q sub T, it would then be just simply a summation, right? The total energy lost for the particular system must equal the energy lost, and I'm putting in the negative sign here. You don't have to because they would all just cancel, but would be the energy lost of the soup minus then the energy lost, right, of the aluminum. And obviously you can make these all positive if you wanted. That's totally fine. I'm going to do that now as I calculate, but I just want to show you the signs there because the signs actually will become important later on in the problem. So here we have the total Q, okay, will equal then the Q of the soup. So it's the mass of the soup multiplied by the specific heat of the soup multiplied by the change in temperature of the soup. All right, and that's then going to be added now to the mass of the aluminum plus the specific heat of the aluminum plus then the I might be saying plus, I don't even know what I'm saying, times the change in temperature of the aluminum. So in order to get to freezing, what's the temperature change? If you start at 25, what do you got to get to? Yeah, you got to get to 0. So we know actually the final temperature here in my question basically. So we're just doing a test. So it's the mass of the soup, 0.8. Multiply them by the specific heat of the soup, which is that of water. So it's 4184. Your book uses 4186, but I'm so used to using 4184. And the specific heat changes anywhere with temperature. So go figure. So the temperature change now is going to be 25 degrees Celsius all the way to 0, right? So it's a subtraction there. Oh, sorry. What am I doing? Well, technically it's the opposite, right? So it's going to be 0 minus 25. Okay, great. And then this is going to be plus now. The mass of the aluminum they told us was 0.25 kilograms. The specific heat of it, you got to look that up, is 900. And then the temperature change again is 0 to 25. So let's just calculate this first. Let's see what we get. All right. And we're not doing all this necessarily for naught because we're going to need this anyway. So 0.8 times 4184 times then essentially negative 25, right? Or you can just say 25 for now. Then plus 0.25 times 900 times 25 again. And they're both going to be negative, so they would just add anyway. So it's going to be negative overall, and that should make sense. It should be negative. So there's going to be 89305. So 89,305. And that's in terms of joules. Now, this is the amount of energy it would take to get to the freezing point of the soup. Right? It would have to lose this amount of energy to get to the freezing point. But now in the problem, and remember, this is about 89 kilojoules. Okay? But now it's telling us that the whole system actually lost 377 kilojoules. So now I know for a fact that there is a phase change, right? I'm essentially not done yet, okay? I'm not done yet. The system will lose, in order for this bowl of soup with the aluminum to get down to 0 degrees Celsius, it would have to lose this amount of energy that I calculated, okay? Now, I'm actually going to put this aside. So let's actually put this aside. I'm going to put it at the top. Okay, so it had to lose that amount. All right, cool. So now, if I go back to my diagram, I basically found from 25 degrees Celsius up to 0. Okay, I just drew in my line up here, guys. Pay attention. I don't know if you are or not. Sometimes when I write something, I think it's apparent, but then if I look back and I'm just watching to make sure I'm drawing lines, and I'm like, I don't even know where I'm drawing them, and I'm the one that did the video. So anyway. Sure. So I found that part of the problem, and we'll also associate the 89 if you wanted roughly. Yeah, I'm just gonna leave that out for now. Well, you know what? Screw it. I'm gonna put it in. Sorry, guys. 2 seconds. So we'll also then say that this is about negative 89.305 kilojoules, just so we can easily compare. All right. So now, what's going to happen next? So now let's talk about the phase, the energy that has to be released in order to undergo a phase change. Let's see what that gets us, okay? So now part 2 is the energy lost during the phase change, okay? We know it's going to freeze. We're certain now because we have to lose more energy than we would have only lost to get down to the freezing point. So we're going to keep losing energy, it says. So the energy lost to freeze. Remember, this is constant now at 0. All right, so basically what I'm doing now is I'm finding this part of the problem. Okay, I've done this diagram before, so take a look back at a couple other videos. I explain the diagram a little more in detail. So now, in order to calculate this during phase change, we got to use that formula over there on the right-hand side, right? It tells us now that the heat associated with a phase change will equal the mass of the object undergoing the phase change multiplied by the latent heat of vaporization or fusion, depending upon what you're talking about. So in this problem, we're talking about a freezing, right? So we're talking about the heat lost, basically, for freezing. Now, the signs are not going to get spit out here, basically. You have to know that it's lost, so you can just plug in a negative at the end. Or you can make your heat of fusion negative. It doesn't really matter. Here, then the mass of the phase change, so it's the mass that has frozen, okay? Multiplied then by the latent heat of fusion, okay, of the soup, right, which is that of water. Now here's the thing, when you do the mass, and that's why I keep putting in these subscripts and I keep explaining the terms, and I try to, as best I can, always keep talking out the formulas. Because what is the mass that should be going in here? What mass should this be? It should be this mass. Only this mass. Not the combined mass. Just the mass of the soup. Because what's freezing? The soup, not the bowl, right? It's already a solid. The aluminum bowl is already solid. It's already quote-unquote frozen. All right? So remember, freezing just means that we're turning liquid water into solid water, okay? So let's now plug in the mass of the soup. So 0.8, right? You got to be consistent. That's the most important part here. Multiplied by the latent heat of fusion. That's of water. This is like memorized, right? This is about 334 kilojoules per kilogram. You can look that up on the tables. So now let's see what we get. So we're going to get 0.8 times now 334. So here we get about 267. Okay, 267.2 kilojoules. 267.2 kilojoules. Okay. Now, this is the amount of heat. This would be negative, okay, because we're freezing, so we're losing energy. Now, we talked about here that undergoing the phase change now, the freezing part, or I could call this the phase change P, we would have now lost 267.2 kilojoules. Now, take a step back, okay? Will the temperature continue to drop of this bowl soup thing? Well, you now say to yourself, well, we lost this amount of heat when we went from 25 degrees Celsius down to 0. And now undergoing the phase change, we had to lose this amount of heat just to freeze the liquid water, to turn the liquid water into solid water. So why don't we actually add these two together and see where we are in terms of total heat lost? Okay, so let's add them together. 89.305 plus the 267. So we're at 356.5. So right now, as we stand, we are at a total, if I were to summate these, right? I'm just summating these two. Right now, we are at a total of 356.505. 505 kilojoules. This is now the amount of heat that has been lost. Okay? Total. At the moment. But notice, we're going to lose even more than that. 377 kilojoules. We've only lost 356 kilojoules on average, right? So what does that mean? That means now the solid is going to now continue to go down in temperature, right? We still have unaccounted about 20 kilojoules of energy that's being lost. So now, this is part 3. So now we know in terms of our diagram, we are entering now this phase of the problem. Okay? And the thing is, where do we end? That's the whole goal here. Now we can finally get down to the calculating this final temperature. All right, so part 3 is finally now final temp. Let's get down to it. Okay? How much heat is left? And by the way, there's many ways to approach this problem. I like to think about it this way in a series of steps. I could have created one formula at the beginning for you too. There's a whole bunch of ways to do it. This way I think is a little longer, but I do believe that this way illustrates the concept better. I think you'll understand it better. So remember, as I was mentioning before now, we have how much heat energy left to be lost. Well, we can take the total heat, right, of the 377 kilojoules. And we can now subtract out the heat that was already lost, which was 356.505. I'm using very exact values here. So we can now find, so we get 377 minus then that answer. So we got about 20 and a half, as I was mentioning before, right? We have about 20.495 kilojoules left to lose. Okay? This is the amount that's left to lose. Left to lose. Okay? I'm just going to put that aside for the time being. Let's bring that on down to the bottom. So now let's set up the next part of the problem here. It's going to be identical to, almost identical to, the initial part of the problem, okay? Whereas we do this. The total amount of heat energy lost, will be equal to the amount of heat energy lost by the soup, the solid soup this time, minus the amount of heat lost by the aluminum. The aluminum's still solid, so that really doesn't change from before. So now I'm just going to make everything positive since they're all negative, right? So this is now the Q, the total Q, all right, will be equal to. Now, when I say total Q, what I'm saying is that, well, let me just write out the formula first. So this is now going to be the mass of the solid soup, which is just the mass of the original soup, right? Whatever was liquid turned into solid. Multiplied then by the specific heat of the solid soup. That might change. It might not be the same as the liquid, okay? Multiplied then by the change in temperature of that solid soup, okay? Plus now the mass of the aluminum multiplied by the specific heat of the aluminum multiplied by the change in temperature of the aluminum. Okay, so now let's start to plug in some of the values. Now remember, this represents the total amount of heat left to be lost. Okay, we already took into account the two heat losses prior to this point. So the only thing that's left to lose is what we found down here. Plug in the negative sign with this, all right? It'll give you the right magnitude and the right final answer. If you were to not plug in the negative sign, you would get the right magnitude, but the answer might not totally make sense. You might say, well, wait a minute, that's now positive. How can that be? It should be less than zero, negative. You would be right, the right magnitude, just the wrong sign. So you could do it either way. I think this way is a little easier. Now, one other thing. This is in kilojoules. Okay? Once you start using this equation, you could use kilojoules, but you got to make sure then that the specific heats are in kilojoules too. All right? Which they're normally given to you in joules. So that's always part of the complexity here. So I'm going to convert this into joules, just multiply it by 1,000, right? So this really becomes 20,495. All right, that's equal to then the mass of the solid, which is 0.8, right? The mass of the soup, that is, multiplied by the specific heat of that soup. Now it's a solid, so the specific heat changes is going to be about 2090. It's similar to ice. They said to use water as the approximation, so you can look that up in the table. And then minus the change in temperature. Do we know the change? No. But what do we know? Changes are always final minus initial. So take a look at the diagram up here. Do we know the final temperature? No, that's what we're trying to find. So let's just leave that alone, TF. Minus then the initial temperature. Do you know the initial temperature of this part of the problem? It's just the part in red. Sure, it's 0, right? That's why this is kind of nice. It breaks it up into nice little pieces. Plus in the mass of the aluminum, they told us was 0.25. The specific heat was 900. And the aluminum again. The final we don't know, and is going to be minus 0 because that's what we're starting with. Just erase this at the bottom to make a little more space. And now let's begin to calculate. So this is 20,495 joules now is equal to, so let's do that, 0.8 times then 2090. So this is 1672. So 1672 times the final temperature, because TF minus 0 is just TF, right? And that's all multiplied then. Plus then 0.25 times 900, so a quarter of 900. It's about 225, I think. And multiplied by TF again. So if you notice, right, this is starting to make a little more sense. It's saying that the total amount of heat left to be lost should be equal to the amount of heat, lost by the soup plus the amount of heat lost by the aluminum. Okay? So it's starting to hopefully make a little more sense. So now we combine the like terms. 1672 plus then the 225, we're going to get 1897. 1897 times the final temperature. And now you just got to divide out the 1897 from both sides. So let's do 2495 divided by that answer. And we're going to get about 10.8. Okay? So the final temperature, negative that is, right? The final temperature now is negative 10.8. All right? Degrees Celsius. Now this makes sense with the sign, right? It should be negative. It should be less than 0. If you didn't plug in the negative sign here, right? Your answer would have been right in terms of magnitude. It would have been 10.8, but it would have been the wrong sign. So you could just think about it then logically. Obviously, it can't be positive if we're losing heat still. Okay, it can't be going up from 0. So in any case, Voila. Right, here it is. Here it is, ladies and gentlemen. Okay? So, long problem, many steps, but I hope it makes sense. All right, breaking it up into several pieces, I think, instead of combining into one equation at the beginning, which we could have done, I think highlights different aspects of problems like this. And hopefully that should help you on problems that you haven't seen before. All right, that's really the ultimate goal here. Guys, thanks for tuning in. I appreciate it very much. Please remember to subscribe, and we'll see you next time. Thank you.